Hi, this is Crossdot and Nabla, and in today's video, we're going to be covering over section 13.3, double integrals in polar coordinates. So in our past two videos, we've been covering over double integrals, right? So we've been covering over double integrals in rectangular areas and double integrals in non-rectangular areas. The first video was really straightforward, just your basic integration skills applied to multivariable functions. And the second video required a little bit more spatial thinking with regards to how to actually order your integration, how to pair your limits of integration and things of that nature. In this video, it's going to be a little bit different. And if you took Calc 2, which I'm assuming you have if you've watched this video, and or if you've taken any like AP or IB math that involved integrating polars, this video will be somewhat familiar to you, but will also have new additions, right? And before we even start, we should just remind ourselves, what do polar coordinates even look like? So if we have a conversion between x and y like this, we get that into terms of r and theta, and we know that x squared plus y squared equals r squared, x equals r cos theta, y equals r sine theta, and theta equals tan inverse of y over x, right? Those are our base ideas that we understand from Calc 2, right? And this is going to be very helpful for us to actually analyze these types of problems now. You might have seen in your Calc 2 class or in your AP Calc BC class, I took AP Calc BC my sophomore year, and I definitely did see this. I don't know if I saw it on the exam per se, but I saw it in our work that we did was this formula right here. And although it is a reductive form of what we're going to be covering over in this video, a lot of cases with double integrals and polar coordinates actually do kind of boil down to this, right? And we can see that through many of our case examples, but sometimes your lower bound for your r, your radius, is going to be not 0. It's going to be 1 or some function in terms of theta, right? And before we even start off with like going through and plugging and checking the integration isn't going to be the concern. The concern is going to be whether or not to use polar coordinates for certain problems, right? And if you may have done certain problems in the textbook that have your bounds be a square root, for example, let's just actually use this right here. We can draw out a little thing like this, and we can say that we're trying to integrate the area from 0 to pi of 0 to root 1 minus x squared dy dx, right? Trying to do this on your own is kind of difficult. Integrating this on your own, like this, is pretty hard. You have to use trigonometric substitution. It's another thing you learn in Calc 2, but it's one of those things that you're going to probably, unfortunately, forget after you take that class, unless you're going back to the material, of course. You're going to have to do a trig sub here, and that's not really convenient for us, right? You can still get the answer, and the answer is pi over 2, but what we're going to do instead is we're going to find a way to more rigorously analyze these types of problems, right? So, in fact, we can actually keep this, and we can have a bunch of different little semicircles like this, right? And ultimately, we're interested in looking from your d, we're trying to convert from your x and y to your r and your theta. And I'll actually copy this over here to illustrate this idea, right? So I'm gonna box this actually. I think it's a significant thing to remember, right? So instead of converting between x and y, dy dx, we're gonna be doing dr and d theta, right? And I'm actually just gonna, let me just erase this real quick because I don't think that's as accurate of a drawing. And these are very pixelated, so apologies about that, but let's jump into it. So let's just do all this right here, right? So I'm going to use a white actually to illustrate this. So I'm going to go from the origin to this, the origin to this. It all starts at a singularity, you know, which is kind of obvious if you've seen polars before. But what I want you to notice is the area that these shapes are making. And that's kind of significant right here, right? So let's just pick some random spot like right here, right? Right? What we're getting is we have our dr. Let's actually use a different color. Let's use blue now. We have our dr right here, right? But then we also have our theta, which we'll mark in green. We have theta right here. We have theta right here. And imagine these slices. These are kind of large slices, right, relative to what we want. We want an infinitesimal. We want an infinitesimal dr and d theta, right? Imagine these thetas are getting infinitely small, right? That's what we're getting at. And we're going to get this to be r d theta because this r right here is different than this r right here. And this r right here is different than this r and different from that r, right? And so on and so forth. And what we're getting at actually is this red area that we just shaded in gets us our conversion factor or our what's the proper phrase that we can use? Our conversion between the dy dx land into the dr d theta land, right? That's our scale factor. That would be the technical term to use. We're scaling dr and d theta with r because as your radius changes, your entire equation is going to be changed as a result. If it was dr d theta equals dx dy, that's not how you get to these equations right here, right? So that's something we have to be conscious of, right? And now we can say that this right here, this red, we'll just mark it somewhere like right here, I guess. This red right here equals dA, right? And normally we would think about it as a dy dx. We'll just write that in green. But now we see that we can just do r d theta times dr. And again, this is kind of a rudimentary example, but if you scale it small enough, you would get dr times r d theta base times height. You get r dr d theta, right? So then that's how you get this conversion factor. And in our section about the Jacobian, actually, we're going to be covering over what this would look like, how to actually solve for it using matrices, right? And again, we have this equation right here, this area of a sector we've seen before, right? And that's how you would also calculate the area of a part of a circle, right? A part of a circle, right? And in essence, this delta theta just replaces with the d theta because it's an infinitesimal change, right? What if you don't have a circle? What if you have a cardioid, a lemniscate? And we'll see those examples, see those types of polar curves in this section as well, right? Perfect. To now actually get this understanding down, we have this right here. So we're going to be finding the area of the given region S by calculating the area equal to double integral over the region S, dA, which equals r dr d theta, which also equals dy dx or dx dy, right? However, we know that there are going to be certain cases, as you might have seen when you were doing your practice problems or whatever, that there are going to be problems that are way easier to do in polar coordinates and way easier to do in rectangular coordinates. Just like in our last video when we talked about changing the order of integration, if you have to do two double integrals instead of one, that's an inefficient way to get to the answer. If you can just do one double integral, you save yourself some time. And that's kind of the idea here, right? You can figure out what's more effective, what's going to save me more time solving for these types of problems, right? For example, 1a, we have S is the smaller region bounded by theta equals pi over 6 and r equals 4 sine theta. So if you want to try and do this on your own, I would recommend getting some graphing paper out and maybe get polar graphing paper out. I don't know if you would have that on hand per se, or you can even use Desmos to look at this and analyze it. But let's jump right into it. So I'm not going to even start integrating yet. I'm going to be looking at this curve on Desmos, which I just have right here, right? And part of it is we have our bounds, right? So we have r equals 2 and r equals 4 sine theta, right? And I obfuscated the bounds for a second real quick just to highlight something, right? We want to look for the intersection, right? And they intersect at this point right here, this green point right here. I could have labeled it, right? But it's going to be 2 comma pi over 6 in radians, and then root 3 1 in Cartesian coordinates, right? Now we can see this is the area we want to calculate right here, right? We want to calculate from 0 to pi over 6 for our theta, and from 0 to 2, or no, 0 to 4 sine theta, excuse me, for our r, right? So now we can go back to here. We can do 0 to pi over 6, 0 to 4 sine theta, r dr d theta. You can do, now we can do our integration. I'm always going to go back to the red because I think it's easier just to tell when I'm integrating and when I'm not. So then we have this right here. We're going to have 0 to pi over 6, and I see an r dr. That's the first thing, so we have to look from inside and outside. It's like an onion, right? So then we're going to do r squared over 2, evaluated from 0 to 4 sine theta. And then the d theta comes out at the end, right? In this case, we can go over here and then evaluate this. This would become 4 sine theta squared over 2 minus 0. We obviously know what that is, right? And then we would get 8 sine squared theta as our resultant answer. But we're still not done. We still have to integrate again. And in this case, it's going to have to call back on your either most loved or hated identities you might have had to memorize. Your half angle and double angle identities, right? I wasn't a particularly big fan of memorizing this back when I did it in pre-calc. It was not fun, but you have to do it sometimes. And we'll actually just pull up the equation right here. I'll write it in green actually, because I feel like we need more colors in our life. And we're gonna get theta over 2 minus sine 2 theta over 4. Yes. Yes, that should be it, right? Yeah, perfect. Okay. Now we can go back to integrating. We have 8, right? So then we would say that this is going to be 4 theta minus 2 sine 2 theta, 0 to pi over 6 d theta. And then you would integrate this as well. And then our resultant answer would just come from taking the antiderivative, right? So we would get theta, we would get, let's just double check ourselves real quick. Did we miss anything beforehand? Oh, actually, no, sorry. I made a mistake. I got the antiderivative. I was looking at my notes and I realized what I was doing. Yeah, so it's gonna be 1/2 minus sine 2, 1/2 minus cosine 2 theta. I was like looking at myself like that's confusing to me, right? Yeah, there you go. This makes more sense. Yes. Okay. See, even then, even if you are prepared and even if you are looking at something ahead of time, always making mistakes. That's something I've been reiterating in these videos. Always check yourselves. This should be a 4, and this should be 4 cos 2 theta. This is going to be 4 theta minus 2 cosine. No, not 2 cosine. It's going to be 2 sine 2 theta. If I do it from 0 to pi over 6, right? There you go. Yeah. And this is going to become 4 pi over 6 is 2 pi over 3. So then minus 2 sine of pi over 3, which is just going to become minus root 3 minus 0 minus 0. And then our resultant answer is going to be 2 pi over 3 minus root 3. Perfect. And then we also have to calculate the area of the given region S by calculating the integral. S is the region outside of the circle and inside the lemniscate. All right, if you want to try this on your own, feel free to pause the video. I'd recommend looking at Desmos before you do so. And let's get right into it. All right, here I am on Desmos trying to solve this equation right here. And before we even start, one thing I want to know, I already have these things done ahead of time, but we're just going to get rid of them because I think it'll help our understanding, right? A big thing that you can look for in this section, but not in all sections of integration, multiple integration, is applying symmetry. Applying symmetry is probably one of the easiest way to just save yourself some time. Besides choosing which coordinate system you choose, right? Whether it's Cartesian, polar, or spherical, right? In this case, we can see that this is perfectly symmetrical, or about theta equals pi over 2, right? So why waste our time writing out two separate double integrals when we can just consolidate into one and just multiply it all by 2, right? We're not going to waste breath on that, right? And I hope we don't, because there are other things we can do with our time. Doing that, the procedure, of course, is still the same. It's just going to take us more time, and it's more mechanical, right? But then again, we still have to find what area we even want to integrate, right? We want to find our upper and lower bounds for our R. So remember that S is the region outside the circle and inside the lemniscate. So the lemniscate is this red function right here, and the blue is right here. So we want the area in between. So like, we want this whole thing. I'm just kind of gesturing at it. I probably should have done something with that, but we want something inside here. You can see my stylus moving, I guess, moving the screen around. This is the area we want, and we can actually use our values to solve for that. And we can actually get back to it now. Perfect. So we want to solve for our theta, where we can actually integrate, and we know that the lemniscate is going to be the outside function for r, and then the r equals 2 is going to be our inside function for r, right? So we can plug in r for both, and we get 4 equals 9 cosine 2 theta. We get 4 over 9 equals cosine 2 theta. And we do cos inverse of 4 over 9 equals 2 theta. So we get cos inverse of 4 over 9 over 2 equals theta. That's our theta that we're going to be looking at, right? And it's going to be from 0 to theta. So we'll just call this theta, right? Just going to save ourselves some time. And we know that for our value, so we're going to call it 0 to theta, which we've already defined. Actually, we'll just call it theta 1. Theta 1 is technically what we can just plug into Desmos, because our other graphing calculators, to save ourselves some time, right? And for our second one, we're going to do 0, not 0, it's going to be 2 to root 9 cosine 2 theta. And the reason why we chose the square root is because we're going from r, dr. We're not integrating with respect to r squared. We're integrating with respect to r, right? So taking the square root just makes our lives a little bit easier, just, save some time. And it'll actually work out as we go along. Okay, let's jump into the integration. Let's try not to go too quick, but, a little bit of speed never hurt anybody. Actually, it does, so I probably shouldn't even be saying that. Anyways, we have this right here, and we're evaluating from we're evaluating from 2 to root 9 cosine 2 theta. And then we get to this part, we have to actually evaluate it, and it's going to be the square root of this whole function minus 2 squared over 2. And then we would get our resultant equation, which is just going to be 9 cosine 2 theta over 2 minus 2. And one other thing that we're going to mention is that we're going to actually have to double it because it's on both sides. We're looking at not only one side, but both sides, right? So we have to consider that as well. So we have to multiply this by 2. So we're going to have to add an additional 2 right here. And then this is all going to be multiplied by 2. So then we're going to get down to here. We're going to get 9 cosine 2 theta minus 4, 0 to theta over 1 d theta. And now this is at the point where you can just plug this in on your own and solve for it. Or you can do it algebraically, knowing your inverse trig rules. I'm not going to do that because that's more technical than I would even prefer for these types of problems. The bigger point of this video is to show how to do double integrals. But I can write out the answer as a result of that. I'm going to get 65 over 2 minus 2 cos inverse of 4 over 9. And perfect, yes. Using example 2, A, B, and C, try these problems on your own. And for 2C, we're actually going to be converting from Cartesian to polar coordinates because these save ourselves a lot of time. And let's jump right into it for all 3 of these examples. Okay, so for example 1, I have these bounds. I think the bounds for 2A and 2B are going to stay the same, so we'll just write it out somewhere. I'm going to use my red for my graph. It's kind of a bad graph. You need to make it more straight. There you go. And then we have the region S in the first quadrant, so we know what this means. 0 is less than or equal to theta, less than or equal to pi over 2. So we know this. So we know that this is r over 2, r equals 1. And remember that this is going to be r squared. So this is going to become r equals 1 and r equals 2 right here. And now we have all the steps and all the tools to integrate now. But before we even do that, we have to convert this y right here to polar coordinates. And we know that y obviously is r sine theta, so we don't have to worry about that. But it's always good to double check ourselves. 0 to pi over 2, 1 to 2, r sine theta times our conversion factor r dr d theta, which again is equal to dA, which is equal to dy dx, right? I'm repeating myself, I sound like a broken record, but this is also really important to remember as well, that your conversion factor, right? What that means in this case. And then we can rewrite this now to actually start this up. We have our integral again. R squared sine theta dr d theta. And in this case, actually, what we know is that sine theta is actually constant with respect to r. We can pull that out and integrate that separately. If you want to choose to do that for your problems, feel free to do so. But I am not, because I already struggle as is in single variable, not single variable, in double integrals and rectangular coordinates. Can't really process that, so this is way too much for me. But if you want to do that, feel free. But you're more at risk to make mistakes, right? Going back to our actual work, though, this is our antiderivative evaluated from our bounds, and then we get 2 cubed over 3 minus 1 cubed over 3, 7 over 3. Perfect. Let's bring this down here. We got 1 to 2. Actually, not 1 to 2, excuse me. We already did that. Oh my gosh. 0 to pi over 2 sine theta d theta. Right? And now we can take the antiderivative of this, negative cosine theta, 0 to pi over 2. This just becomes 0 minus negative 1 plus equals 1 times 7 over 3. And then you get your answer, which is 7 over 3. Perfect. Example 2b, we have to convert again. It's the same bounds, so we're just going to rewrite the bounds for our integral again. And again, these double integrals are kind of a mechanical process, but it's still a valuable exercise to undergo. r cubed dr d theta. And this is r to the 4th over 4. Let's move this over because I want to actually write the integral in the bounds from 0 to pi over 2, 1 to 2 d theta, right? And then we can actually plug and chug our numbers. So we're going to get 2 to the 4 over 4 minus 1 to the 4 over 4. And then we get 16 over 4 minus 1 over 4 equals 15 over 4 as our final answer for our first integral. And then our second integral, we just have to plug and chug for that. 0 to pi over 2, 15 over 4 d theta, yeah, which is now 15 over 4 theta, 0 to pi over 2, and then we're just plugging in more, 15 pi over 8 as our final answer. It's not so bad after all. And evaluate this using polar coordinates. If you want to try doing this in rectangular coordinates, feel free to do so. But I will say, out of all of the work we've done so far and all of these videos, I would say that this would probably be the most difficult problem to do in rectangular coordinates. But again, if you want to try, feel free to do so. If you want to post a solution to this in the comments, feel free to do so. And let's jump right into it. So it's dx dy, and we have our equation. So I'm going to have our bounds written like this. So we know that okay. And we have 0 is less than equal to y, less than equal to 1. Okay. I'm going to see what I can do about this portion right here. Let's see. So I'm going to say that x equals 1 minus y squared, because we're just going to have to assume they're equal, because those are the endpoints where the limits, the boundaries of the limit, right? Oh no, sorry, this is square root, yeah. But in essence, I actually did get to the answer before I even realized, but I'll just show it in full. That's what ultimately what matters. Square both of these. You get x squared equals 1 minus y squared. X squared plus y squared equals 1, right? And then we can graph out our equation, and then we can graph out our circle in blue, kind of a sloppy circle. But we know that from our equation that 0 is less than x, so we have to completely ignore this section, right? And we have to also consider that 0 is less than y less than equal to 1, so we have to ignore this section as well. So then really all we're left with is this section right here. And I'll start with that in white right here, which we know just by looking at it would be from r's, so like this, and then pi over 2. And then we know that this is going to be r squared. And we're going to see a cool trick actually to save ourselves some time in solving this problem. And then we got sine r squared, and I'll write that like this, r dr d theta. And now we're going to pull out one of our best friends ever in calculus, the u substitution. And we can do this, du equals 2r dr. And now we can plug and chug. So let's get back to this, 0 to pi over 2, 0 to 1, because if we plug in 0 squared is 0, 1 squared is 1, right, just to make sure. Then we have our r sine of u times, I'm going to write this in white just to be extra clear what the u sub is going to look like. It's going to be du over QR d theta. And this r and this r will cancel out. And then we're going to get this as follows. And I'll actually rewrite this in red again. So we're going to have now 1/2 0 to pi over 2, 0 to 1 of sine u du d theta. And the d theta is going to be constant to everything. There's no theta, so we can just leave that as is. Or we can actually just do it right now. It's going to be pi over 4. It's a shortcut, but we know that's a constant, right? We get sine u du from 0 to 1. Our antiderivative of sine is negative cosine, as we've seen earlier. We're going to get 0 to 1, and we're going to get negative cosine of 1 minus 1, minus, actually not minus 1, minus negative 1 plus 1 minus cosine 1 is our resultant from that integral. We'll multiply that by pi over 4, and I'll actually write it down here again. So it's going to be pi over 4, 1 minus cosine 1. And that is our resultant answer for this last integral. And that is the last problem that we're doing in this section covering double integrals and polar coordinates. In our next video, we're going to be covering over triple integrals in rectangular coordinates. In the video after that, section 13.5, we'll be covering the 3D version of polar coordinates, aka spherical and cylindrical coordinates. One last thing I would like to add to for that is I think it would be fair to say that cylindrical and polar coordinates are basically siblings, but spherical and cylindrical and polar are all cousins. They're all related, but one's closer to the other, right? And that is it. Thank you so much for watching any of these videos, even if it's just this one video. I really do appreciate the support. Thank you so much, and I hope you guys have a fantastic day.